Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks, Josie. So hi, it's nice to be here. I'm going to be talking mostly about adaptive indexing, database cracking, as we call it, in the column store area. And this is work done with people from CWI, Martin Kersten and Stefan Managold, and also people from HP Labs in Palo Alto, Getz Greff and Harumi Kuno. And this is work in the area of how we deal with large data sets, where current techniques in databases, at least, they mostly fail. When you start thinking about how I'm going to index, how I'm going to query large data sets. So let's see what we mean. So self-organizing databases is, I think, a very intuitive term. In databases, we have indices. And these indices are being used to fast query data. But we have a very basic problem. It is when we build indices and which indices we're going to build. So there's a whole community looking into this problem, what kind of indices we should build and when we should build them. And this is a very basic problem. Essentially, if you had all the time in the world and all the perfect knowledge in the world, you would say, these indices I want them at this specific time, and I'm done. But what actually happens is that in databases, at least, we have these auto-tuning tools and these experts in database architectures that they do the following little trick. You get a workload, and by workload we mean a specific data set and a set of queries. And then you do these three little steps there. It's monitoring the performance of the system under a sample of this workload, and trying to predict what the performance of the system would be. And then, seeing all this, you have all sorts of fancy techniques, so you can do the proper physical design. Basically, it's this prepare world there, and prepare means that this is before query processing. So you've done some monitoring, you've done some analyzing of the workload, and then you start preparing. And preparing means I'm going to create these indices now. So all these little steps there, they take time. And they take some considerable time and some considerable resources. And you can do them very well if you have the time to do them and if you have the resources to do them. But what happens if you don't? So what happens in dynamic environments? And mostly what we care about is environments with big data sets. So what can go wrong there? OK, I guess this is not really visible to all of you. The thing is that the workload, the queries, they can change. So it's not always stable. When you create an index, you create it with a specific query in mind. And it's going to cover a set of queries, at least, a pattern of queries. But what if the workload changes? So then this index is not valid anymore. It's not useful, actually, anymore. And having a not useful index means that you spend storage to have the index there, and you also spend resources to maintain the index under updates. So the second bullet is what happens if the workload cannot be predicted. This means that the workload can change dynamically, can change very often. And yes, in the past we didn't have so much of these scenarios, but nowadays we do. And you can think of the web, and you can also think, in our case, what we are mostly thinking of is scientific databases, where people get lots of data, and then they just look at the data and start thinking what kind of queries they should ask. And then depending on the answers they get, they ask another query, and basically the pattern in their minds evolves as they answer and as they take more and more answers back from the system. So there's no initial pattern. Another crucial bullet is, what if there's not enough time to prepare? And this goes here. So there's not enough time to do the monitoring part and basically the preparation part, because all this, they take really a lot of time. And think, again, the cases of huge data sets as we have and we're going to really have in the future in the cases of scientific databases. And I'm talking now about terabytes very often, sometimes even per day, as you're going to have in I think it's 2017 is when the new technology is going to come for astronomers. So what do you do then? In databases, even just loading the data into the database, it takes hours. So what if a couple of hours more, you have even more data, another terabyte? When are you going to do the monitoring? When are you going to do the prediction and the preparation? And there's no time left for the querying part. Update is also a crucial pattern. If you build indices, you have to maintain them. So the data changes. You have to change the indexes that you have in your system so they are still valid for the queries. Otherwise, they're not useful. So if you have indexes that are not useful, you're paying resources maintaining them. And then there's the crucial part of very large data sets. So building an index for a small data set can be cheap, can be fast. You can probably store it in some small little space. But what if you have terabytes of data? What do you do then?
So is your idea to replace the whole predict and prepare thing with an automated system?
Yep.
You just give the database, you do no work, you just throw it in and
yep.
it figures out what indices.
Yep.
Oh, splendid.
So, okay, when I started this, I was a foolish PhD, but...
Sorry, the issue here is the fact is that indices cost you in loading and in space. So basically, we make decisions on indices based on whether or not, if we're loading into an area an awful lot, we're willing to take the cost and analysis. So you've got to take in the loading process as well as the reading process, because otherwise what you're going to do is you're going to make the analysis process cheap, but you're going to considerably complicate the loading process.
Exactly.
To the database.
Exactly. And I guess this is a basic problem in all of computer science. You build a data structure and then you can use the data structure efficiently. But how much time and how much space you need to build this data structure? So, and on top of that, other than the technical part of space and time, you also need the knowledge that you need this data structure in the first place. So, so the vision here was, let's just remove all these restrictions, do nothing at first because we don't have the time and we don't have the knowledge, and let's see what we can do. So, okay, as this is just what I described just now. As the audience also noticed, we're trying to push all this notion inside the kernel itself, inside the database kernel itself, and we're trying to remove all this legacy of monitoring, preparation steps, the human involvement in this task as well, because there's a significant human involvement in this task. Even with our most modern technology nowadays, and Microsoft has done a significant part of this work with auto-tuning tools. These auto-tuning tools, they give you a recommendation. They don't tell you do that. They give a recommendation after analysis back to a database expert, a human person, and then the database expert, so they say, okay, this, and that I want. Oops, sorry. So basically, this line here is the first idea that we started working on. And in our case, this goes in the context of column stores. Because for the last 15 or so years, we built column stores in the CWI database group with a MongoDB system. And I'm going to explain why column stores made this kind of work possible or enable this kind of work. So the idea is that we do continuous, on-the-fly physical reorganization using every query. So if you just see this, there's probably all sorts of things to complain about. So on-the-fly physical reorganization, it already sounds very strange. So typically, in databases, when you get a query, from there on, it's a sacred time. You just focus on the query, and you do only the actions that you have to do for this query, so you can now process the query as fast as possible. So here we come and say, no, we're going to do some physical reorganization as well. So physical reorganization is like physically reorganize the data in memory and on disk. And let's see exactly what we mean. Okay, no, before we see that, I have this slide here which it's basically a very an overview of what we have done the past years for this specific part. So we have a couple of techniques: database cracking, adaptive merging, and nowadays we call it adaptive indexing. And so essentially, we started building a new database kernel from bottom up, and we started working on the left part. You see, so we started with very basic operators like selections in databases. Then we did updates, Tuple reconstruction, which, if I have time, I will talk about. It's a very crucial problem in column stores. So we do all sorts of work, and our goal is to, in the end, develop a full-scale database kernel that, across all database operators, has this notion of self-organizing databases. At this point, as we speak, our prototype is published with MongoDB, so you can download it and play with it if you want. And it does work for these three things here. So you can type queries immediately, and then you get all these ideas that I'm going to talk about, and they just work. So this is mostly the outline of this talk. I'm going to start with talking a bit about data access and rosters and column stores, and then the basics of database cracking. And if there is time, I'm going to go into the sideways cracking, passage sideways cracking, which are some more advanced techniques on how we do query processing. Okay, so I want to spend like 3 or 4 slides on column stores versus row stores. So the way we store data defines the way we can access it. So every time we write an operator in databases or any kind of algorithm, really the way data is stored on disk or in memory or in the caches, it defines the steps that we do. And our database kernels are built this way nowadays. And nowadays we have these nice buzzwords that people are talking about: row stores and column stores, and lately also hybrids. And you keep hearing about this kind of buzzwords from almost everybody. And this is us, and this is also a spin-off of MongoDB, a very recent spin-off of MongoDB, which we sold to Ingress. Which also, like 3 weeks ago, it topped the TPCH benchmark results, which is one of the most big benchmarks in databases. But the main part is that you keep hearing that everybody is trying to do something with column stores, with row stores, and mainly with hybrids nowadays. Because in the end, there's no truth for only row stores or column stores, and the truth is somewhere in the middle. And people are really looking into hybrid stores and hybrid execution models. So let's see some of the basic differences. So in a row store, you typically store data in rows. And you can think of this as being the disk. So you have lots of rows, and then you have columns. So in each row, you have the attributes. And then when you have a query, queries, this is let's say this is a relational table. The queries, each query just refers to a part of these attributes of the table. So what you mostly do is that you go in disk and you fetch this file. And basically, because of the way it's stored, because it's stored one row after the other, you have to fetch everything.
So when you say it's stored in rows, I think you mean that the successive items of a row are physically adjacent to each other.
Yes, that's what I mean. Yes, exactly.
Okay, whereas if you stored it the same picture would do for storing it in columns, wouldn't it? So if you're storing it in columns, then the items of a column would be physically adjacent. Is that right?
Exactly. Yes.
Okay,
yes,
I see.
yes.
Okay.
So, and this is why you have to bring the whole thing together.
You only want two columns.
So, if we do exactly the same example in a column store, so this is our columns, and this is physically adjacent values. Then again, the same query would come, and then we would have to just bring the parts that we're really interested on, because we can just fetch it independently.
Is there an issue too that if a column contains, say, 5-bit values, then you could kind of, if you had a column all of 5-bit values, you could pack them very tightly.
Exactly.
Whereas in rows, that would be more awkward somehow, because then you'd have a 5-bit value and a 7-bit value, and getting them out would be much harder.
Exactly, exactly.
Is that
So this could be, this could be 16 bytes, this could be 2 bytes, this could be 1 byte, this could be, and there are, okay, typically in rosters, you have what we call variable length fields, because you have one attribute after the other of each tuple. So the first attribute could be 16 bytes, the second could be 2 bytes, but then in the in the next tuple, the first attribute could have a different value, but still you might spend 16 bytes to store it. In column stores, you can do basically what I'm trying to say is that you can do basically better compression, because here we just have this is physically adjacent. And we just have the values for this specific attribute, which means that probably the value distribution is quite similar. We can probably do better run length encoding. This is basically the same type. So this is only integers, and this is only strings, and this can be only floats, and we can do all sorts of tricks to nicely pack it together. And in column stores, it's a very big deal that these are fixed length. So each column is it can work with variable length, but every efficient implementation uses fixed length. And the idea is that when you scan these columns here, if they're fixed length, they are arrays. So let's say a simple selection over here, it's just you just get a pointer and you say, I see this value, increase this pointer 1 position, and it's integer, so you don't have to do anything. You just increase 4 bytes, let's say, or 8 bytes, and then you're done. So you can write operators in the matter of 2 or 3 lines of code, very efficient with very nice access patterns, with very nice temporal locality for your data and things like that. And this is one of the really main differences between column stores and row stores, but it's mostly adapting to new hardware and things like that. So here you noticed the query is interested in 2 columns, and we just brought 1 here. So we have the flexibility. I just brought 1 column here, and I can process it, and then only then I can bring the next one. So you can also have, you can always, by having columns independent from each other, you can always bring the part that you want, drop it, then bring the next one, and go on. You don't have to bring. So it's not only that you bring only the columns that you need. You can bring independently 1 column after the other and be even more efficient in terms of memory requirements of your system.
But that's only true if the operation never needs both columns at the same time. I mean,
so
imagine you were to add the columns. Then you can't just process them in one go.
You can.
Well, okay, if you keep a cumulative sum, but
so yeah, this is a big discussion. So the MonadDB system that I mentioned, what we do is that we bring 1 column at a time. We run a complete operator over this column. So in databases you have operators like I select something and then I do an aggregation, let's say, okay? So we can do first the complete selection, and only then we can do the aggregation. This means that, let's say we do a selection here and an aggregation here. We can first bring this column, scan it completely, do the selection, and then take the intermediate result and run the complete aggregation. This is completely different from what is being done now in row stores, in typical systems. And okay, this doesn't have to do with row stores and column stores. It's just past technology and new technology, basically, where in typical traditional row stores, you take 1 tuple at a time and you pass it through the complete operator tree. So the selections, the aggregations, the joins that you have, and then you take the next tuple and you pass it again through the complete thing.
But where are the intermediate results of each single operation in this way? Are they
So-
in disk or?
So in a typical row store, the intermediate results are very small, right?
No, in columns one.
You have to materialize them. You have to materialize them. So then you have a memory overhead because you have to materialize these intermediate results. which is why, so in the MongoDB kernel, we actually materialize everything. So one operator will materialize the complete intermediate result and then go to the next one. In the vector-wise technology, it's basically you're trying to find some intermediate solution. So you take, instead of taking one tuple at a time like you do in rosters, or instead of taking the complete column like we do in MongoDB, in vector-wise we take a batch of each column. So we take a part of this column and then go to the next operator.
To avoid that you hit disk because you don't want to hit the disk for intermediate.
Yeah, it's basically these pieces they fit in the caches, and you can actually amortize the function calls that you do, because every time you call an operator you have to do a function call, and in rosters you do a function call per tuple basically, per operator, which is very expensive. In our case, for MongoDB, we do basically one function call per operator, which is extremely expensive, but then you get the intermediate results materialization problem. So vector-wise finds some intermediate solution there. Okay, so I think the next two slides probably is the discussion that we just did now. So, is it that column stores they're good because you can access data better on disk? And the answer is no. So, as I said, in typical systems we process one row at a time, and it has a very high overhead because you have to carry the complete tuples, from disk, in memory, in caches, in registers, and you have the functional overhead of every operator has to say, give me the next tuple, give me the next tuple, give me the next tuple all the time. And of course, but the main thing is here, you have tons of cache misses just because you carry everything together, although you don't need it. But definitely it's low on memory needs because you don't have any intermediate results, basically. And actually, if you go back like 40 years or so into database technology, you would see that some of the early systems actually failed because they had the strategy of materializing intermediate results. So this was a good idea in the past, but it's probably not the best idea nowadays. So in rosters, let's maybe even use the word traditional rosters. There's processing of one column at a time, and in a block model, as I said, one operator at a time.
What's the difference between a volcano model and a block?
So the volcano is this is a terminology in databases for this pipelined model. So you take one tuple and you pass it through all the operators, and then you take the next one and you pass it through all the operators, and so on. So that's the traditional volcano model. So with one column at a time, you can carry in your memory hierarchy only what you need. So this, you can think about it, I have a selection, I go to disk, I fetch this column A, I move it to memory, to the cache, to the CPU, and then when I reach the CPU, there's only the values that I need. There's nothing else. It's only values of A. The vector-based operators is the example I tried to give before, where you do basically array-based operators, which is very efficient implementation. And I'm going to show a very small example later. And then there's maybe another thing is the optimization decisions, which is quite a nice one. So when you think of it as follows, when you process one row at a time and you move it through the operators, typically, the operators are initially logical operators, but you also have to decide the actual algorithm for each operator. So say when you do a selection, you might choose to scan the data, you might choose to build a hash table and then probe the hash table, you might choose to sort the data and do binary search, there's tons of options. When you do a join, you might choose to do a hash join or do a sort merge join. So typically, you have the optimizer when you get the query at the first place in rosters, and decides the query plan and decides also the physical operators. So it says, you're going to do this operator, you're going to use this algorithm, and then this other operator, and this algorithm, and so on. But choosing the algorithms is obviously a very sensitive task, and depends a lot on the data distribution, and depends a lot on the one operator depends on the answers of the previous operator. So in column stores, when we do the column at a time processing, once we finish one operator, we have the complete result set. And then we can confidently say that for the next operator, we know, because we know the cardinality, we have seen the data, we know we want to use this kind of physical operator. So you can delay these optimization decisions and put them and take them at runtime, and then take more informed decisions. But we have to do the intermediate materialization, as we said. And another crucial problem is tuple reconstruction. And this is actually one of the main problems in column stores, because you have one column at a time, and then you have to combine columns, because queries rarely use one column. They use 2, 3, they use a number of columns. And then you have to combine the data across multiple columns. And this is the problem of tuple reconstruction. And the techniques that I'm going to show also help significantly in basically optimizing and even eliminating this problem in column stores. So, as I said, the tuple reconstruction problem is the one of basically stitching tuples together. And one could think that, okay, how I could do a column store. I could store data per column on disk, and then when queries arrive, I'm going to fetch these columns. I'm going to make them tuples. So I do get the I/O cost, the I/O benefits. I just fetch only the tuples that I need, and I fetch them all together at the first place. And then I stitch them into tuples, and then I can use my typical row store query processing, and I don't have to change my system. So I do get almost all the I/O benefits, and I can still use my past kernel.
So that's if you know that you only need some of the columns. If you needed all of the columns, then you get no benefit at all, right?
No. It depends on the query. It depends on the query.
Can you give an example in which you make a difference? In a query in which you need all the columns, and yet it would be better to load all the columns and glue them into tuples than to just use a row store?
No, I can give an example that this would be better. I can give an example where this would be better.
Right, I was meaning the top one. So the top one looks as if it degenerates to a row store.
Yes.
If you need all the tuples.
Yes, so the top one is like a very fast way to build a column store, let's say. Because you can keep your query processing kernel intact, basically, and you just need an intermediate step that says, go to my column store storage and bring me things, and then make them immediately tuples, so you can use my past kernel.
Okay, and that would perform very similarly to a standard row store.
That would perform in terms of execution similarly to a standard row store, and you would get some of the benefits of fetching data basically more efficiently, because you won't have to load the full columns, the whole columns.
Okay, I don't understand.
No, it's let's say you have 10 columns, and the query needs just 2 of them. Okay.
So I said, if you need all the columns, it would be the same.
If you need all of the columns to be the same, it will be slower actually.
There you go.
Because you have to do the stitching.
All right. Thanks.
Okay, but so what it happens in column stores is that we use this late tuple reconstruction, which basically means that you don't only change the storage, you also change the execution. You have to write a new kernel to have a column store. And these are all the tricks that, and there are many more, all the tricks that we have been discussing so far, the vector-like processing, that the fact that you have the CPU and the cache optimized because you just bring the data that you need into your registers and everything. You can have more efficient vector-wise coding, and you do the bulk processing as opposed to the Volcano. And depending on the query, even if you need all the columns, and if you are going to eventually load all the columns, this can still be orders of magnitude faster than a typical row store because of all the better adapting to hardware properties. So let's now let's see how a column store would look like. So let's say these are the columns A, B, C, and D, and this, I don't know, you like sort of reddish color is the actual values of the columns, of the attributes, and the gray part is the positions, and you can think of the positions. We use them as identifiers, row identifiers, and in memory and in disk, these are just arrays. This gray part does not exist. It's just implicit knowledge. We just know this is the first, the second, the third, and so on. So we don't actually materialize this thing. We just have the arrays of the red part.
Quick question. Missing data is explicitly identified then, I guess, right?
Sorry?
Missing values are explicitly identified?
Missing values? What do you
Like, for example, if the third row of column D was just
Like null values.
Nulls.
Oh yeah, it will be, you would have a specific value for null, just.
Okay.
Sorry, and I have a question. Is this the storage only at the sort of very beginning where your data lives? Because in the pipeline, you might have filtered some columns on some
Oh, sure.
values.
Yes, of course. We're gonna see an exact example of processing a query. So here columns are aligned. This means that yes, I have some. So let's say what would be tuple 5 in a roster storage is the same as going in the fifth position of every column and just seeing the value. So for column C, the value that represents the fifth tuple is C5. And this, I just draw them here just for convenience. They look the same, but as we talked before, it might be different. This might be 16 bytes, it might be 4 bytes, and so on. So if this is an integer of 4 bytes, if I want to go to the fifth position, I just do 4 times 5, and I jump here. This is contiguous in memory in the disk, and I'm here. So it's always if you see a column store code, it's always playing with these positions in the arrays to move across the arrays. So let's do now a simple query. So this is a SQL query. We want to select the average of column C, given that we do a selection on attributes B and A. So we have some very simple filtering predicates on B and A, and whatever qualifies, we want to do an average on column C. So let's, we start with the first select operator that selects over A. And this one will just scan the column and it will create intermediate results. And these are the row identifiers that qualify the selection. And as we were discussing before, this is all it is. This is the code of the operator, just simply scanning the column. And you can see how this is extremely efficient because you just have this column. It's contiguous. It's physically contiguous. And this is exactly as it is. And the results here, now you have to materialize these results, and they just represent these positions. So, so now, after we did this operation, we know exactly the row identifiers of the tuples that qualified from our first selection. And now we have to do this tuple reconstruction action. And this is now an overhead compared to a typical row store. Because what we have to do now is we have to say, given what qualified from one column, we have to go and fetch the qualifying values from the other column. In this case, we have to go into column B, and we do this action. So again, this is very efficient. So as we said, this is again contiguous in memory. We just go to the first position, to the third position, to the fifth position, and so on. And again, this purely depends on the data type here, and we know the data type, so we can just move very fast on the column.
So you said you have to materialize the intermediate result.
Yes.
But do you really? Couldn't these two run as coroutines? The first one produces 1, say, and then 3, and then the second one you can use those values as. In other words, you could stream the result, the intermediate result, rather than materializing it.
Yes. So this is. If you do it one tuple at a time, so you could take the first value and say it qualifies. No. Okay. You can take then the second value, it qualifies. Yes. Okay. Go fetch the B value. This has a very high functional overhead because you have to do all the function calls of doing these intermediate steps. So we found out that it's very efficient to do it one column at a time, do one function call, do the complete operation, and then materialize the intermediate result. Of course. Then we found out again that, okay, maybe this is a complete overkill and there's something in the middle. And this is the vector-wise code line that I talked before, which essentially typically it's L2 cache, It will say how many values fit here, this much, I'll take this much, and then pipeline the operations over there. So you take the first 3 values, let's say, and you run all the operators that I'm going to show you now, and then you take the next 3, and so on. So you try to amortize and to balance the functional cost with the cost of materializing intermediate results. So now we just did this tuple reconstruction. So we found the B values that qualify given the selection on column A. And now we have to do the selection on column B. And because we took this based on column A, then this is also would be it will give us also the addition on both attributes. So now we do again the selection, and then we say, okay, only tuples 1 and 5 qualify. But now we have to do also the aggregation on column C. So again, we have to do tuple reconstruction. So again, we go over the complete column of C, and we fetch the values, and now we're there, and now we can run the aggregation. Again, all these operations are like array operations. So even the aggregation, you can work in a very cache-conscious way over it. But let's see. Let's talk a bit more about tuple reconstruction. So you see this tuple reconstruction thing. It happens very often. Essentially, you have to do it for every attribute that you have in your query plan. It's very crucial that you keep your columns aligned. So you see all these actions here. These are ordered 1, 5, 1, 3, 5, 6, and so on. So you produce these positions as you go through the column. So this is always ordered, at least in this example here. So then you can do nice sequential access over your columns. And doing sequential access is crucial for performance. And also you do positional lookups. So you don't have to actually search where is tuple 1. You just, as I said, you take the number 1, you multiply with the width of the column, which is based on the type, and you're there. So this can be very efficient. But in many cases, as we've seen here, it might actually be spread over the whole column. And then because typically you, even in memory and on disk and on caches, you do batch access basically. You bring cache lines or disk logs, etc. Here in this case, for example, you will still end up loading the complete big column into the caches just to do the tuple reconstruction. Yes?
So it's sequentiality that matters. That's the reason, going back to Simon's question, why you don't want to do streaming, why you don't want to kind of like do this in parallel. Although it might seem like it's faster, it will actually ruin the sequentiality when you actually have to go to the disk, right?
No, the sequentiality doesn't have to do with the parallel processing. The sequentiality does have to do with just being efficient when you access data. Right. You would still do it the same way if you would do it in a parallel way.
How? I mean, if these two columns A and B are stored on the same disk, you're starting to do the query, you're starting to select things where A is smaller than B1. Let's say you got their first result, and now you're going to attempt to find the column in B, but they're stored on the same disk, and the disk really has only one head. So you're better off reading fully A, and then going and reading fully B.
So how you actually would do it is that you would store, let's say, the 100 tuples from 100 values from A, 100 values from B, and so on. So essentially, A would be logically a column, but in practice it will be, physically it will be 10 columns or 1,000 columns, and each one would contain 100 or 1,000 values.
Oh, so A is not physically stored contiguously?
Yes, in this case it would not be stored contiguously, and then you could just load the first column of A. And then all the qualified values would be represented in the first column of B, and so on. And this way, you can pipeline efficiently.
But if they're stored as rows, then they're all contiguous anyway. I mean, you're assuming that everything's got the same number of 1 to 6, and they're all. So you could actually just have one row, which is A, B, C. You've only got one overhead, which is the position. You pull them all in. And they're contiguous on disk, so that's far faster than having 3 separate columns which are distributed around the disk.
Yep, it's faster. In this case, it's faster. So if we, let's say you have a table with 1,000 attributes, okay? And let's say you do a query with that, like we do here, that we only need 3 attributes.
Yeah, that's what you're saying is the fact is that if the number of columns in one table, and the majority of them are never used, then column ways becomes more efficient.
Yep.
Whereas if you're using most of the columns in a table, then row weight becomes more efficient.
Not necessarily.
It could be. So there's.
Well, because they're contiguously spaced. In the
I can construct, and we have constructed so many examples where a row sort would be better. So I'm not saying that columns are better. Okay. I said before that hybrids are better. That's clear. So you could construct so many examples where a row store implementation would be better. And in fact, in hybrid architectures that we're trying to build right now, what we do in main cases is that we do typically all our selections and in a columnar way, and then at some point we reverse on the fly. We reverse our intermediate results. So we take all these intermediates, we do the tuple reconstructions, and we revert them into tuples, and then we go ahead and do aggregations on the fly, because it's simply faster to do these operations in a columnar way. But then it's also a matter of how your kernel looks like, because then you also need dynamic code to do this. It's not simple, but it's true that hybrid storage and hybrid execution is better. So the examples that I'm trying to demonstrate here is the extreme column store example, just to give you the feeling of how it looks like. 5 more minutes. Okay, so then what I'm gonna do is that I'm gonna give the basic example of the adaptive indexes on the adaptive storage. So okay, so we did all these selections before, and we still have to scan all the data. So how you do indices in columns, and how do you do efficient indexes? You could start taking the columns and you can sort them. That's one way of building indexes in a column store, and then you can do binary search, or you can build a tree over a column. So in our adaptive indexing motivation that I showed you earlier, we said that we don't want to do anything up front because we don't know. We don't know which columns the queries will use, and we don't know how efficient our index should be. So we might need 1 query or 2 queries, or we might need indices for part of the column, not for the whole column. So what do we do, and I'm going to give it to you as an example. Basically, each query by the kernel is treated as an advice of how the data should be stored. So let's see here. Let's say we have this selection here, and this in databases this is just one operator, just a select operator, to do this filtering in the workloads. So what we do is that we take this column, and now the operator itself will physically reorganize the column. So you see here the predicates are between 10 and 14. So what we do is that we take all the values that are smaller than 10, and we move them to the first part of the column. And then we take all the values that are actually within the result, and we move them in the middle. And then all the values that are bigger than the result. So now, in this area here, which is again a contiguous area, we have all the tuples that qualify for this select operator. Okay, and now you notice that we actually this select operator doesn't have to materialize this result, because it can just say it's there. It's a view because it's just a contiguous area in memory. And on top of that, and the crucial part is that we just gain some knowledge of how the data is stored, right? Because we know this sort of clustering here.
Do you similarly reorganize the other columns?
That's we're not going to get to that, but yes.
You do?
Yes, but not now. Not now. Now, for this query, we just touch this column.
Okay.
When other queries comes that they need they're on the same table, and they need this column and some other column possibly, then we have to what we do is that we transfer this physical reorganization. We transfer it to the other column as well, in such a way that we can always do sequential access. Unfortunately, I'm not going to get up to this point, but let's go through this, and we can talk later. Let's go through the basic stuff. And as I said, this is happening within the select operator. So this is not an aftermath thing. This is how the kernel works. And then we get another query. And now we can use this clustering information. And this query now says, okay, everything between 7 and 16. And the kernel keeps working this way. So we go into this column and we say, okay, we knew now everything smaller than 10. So the 7 part falls in this area. And we're going to break this piece, again, in 2 pieces. The ones that are smaller than 7 and the ones that are bigger than 7. Now, for the next part, it's all within the result, so there's no reason to touch it. And now we get a benefit because we don't touch data. And again, similarly, we split the next part based on the next predicate. And again, what we do is that we collect all the results in a contiguous area. And of course, we gained even more knowledge, which we can use in future queries. So in some ways, you can think of this as, as an incrementally sorting the column, because these are ordered, but inside this piece there's no order. But it is completely reacting to the query workload. So you really focus in the value ranges and the parts of the columns that your queries are interested in.
I'm worried about how you connect it up to the other columns. If there was a column B and C and D, then you've sort of scrambled column A. So how do you reconnect it with the original columns, which have not yet scrambled? Do you store pairs, the index and the value?
So what you do is that I need 15 minutes to tell you that. So what you do is that again we changed. So this was the second iteration of this kernel Tuple we're building, and this is the sideways cracking part that you saw in the outline. Sideways in the sense that you move sideways in the columns this reorganization information. So what we do is that we take then pairs of columns, and then we always have a leading column. So let's say it would be AB, it would be a pair, and AC it would be another pair, and AD it would be another pair, and then we always work in pairs of columns. So if you would, and each set of pairs is always having a leading column that defines the reorganization. Okay. So then all these pairs of columns will be reorganized based on the selections of attribute A, and then inside you do further filtering. And again, across all these pairs, you adaptively move the reorganization part. So a query comes on AB, you take the pair of AB, you do some reorganization, then a query comes on AC, and then you first synchronize these columns physically, so the tuples are aligned, and as long as the tuples are aligned, you can give back correct results. And then you move on doing further reorganization. So, okay, that was 1 minute, but it's a bit more complicated. We can discuss it.
Maybe I'll do the question after this slide.
Okay, so this is a very simple example showing some basic performance of how this looks. So this is having a 10 million column of integers and doing 100K completely random selections. Random in the sense that everything is completely random. So the selectivity of the quiz is random, and also the value ranges that you ask in the quiz, everything is completely random. So no index has been built up front, and the green line here, the green curve, represents the standard scan functionality in a column store. So you always scan the data, and the red curve here represents the cracking stuff that I have been talking about. And this is you see that the more queries you answer, this is the queries and this is the response time, the more queries you answer, the better the performance becomes. And this is the reason. The reason is that you touch less and less data because of the clustering.
So I get this. If you ask a lot of queries, then your bin size, the size of your little grey boxes, is going to degenerate to 1.
Yes.
So now finding the right bin is solving the original query.
So we don't let this happen because there's a couple of reasons. First, when the pieces become really small that they fit in the cache, then we just sort because you do a quick sort in the cache and then you're done. The other problem is that if you start having a tree, because we built a tree to maintain the index, if you start building a tree over each specific bin that you have, and each bin is just size 1, then simply the cost of searching the tree to go there, it explodes. Okay.
Exactly.
So, but then there's other problems. So the more pieces you have, the more of these pieces you have, this means that the more knowledge you have, the more clustering you have on your columns, right? Which becomes a problem during updates. Because as I said, we also have contiguous, we're going to have everything contiguous in memory. So the more pieces we have, the more we have to shift around during updates. And then also during updates, we drop pieces and so on and so forth.
So this might be done. I was just thinking, kind of on the spot here. Like if I was Oracle, okay, why not go for something much simpler? Given the data is already replicating multiple times, right?
Mm-hmm.
Why not have? Maybe this is a very naive question. So why not have just one of the copies be stored as a row store, and the other copy be stored as a column store? So if certain parts of the workloads want to access the row store part, you know what I mean? So you have multiple copies anyway.
That's what people started doing. So this was actually a paper from Wisconsin, I don't know, 15 years ago. Fractured mirrors, it was called. So yeah, this is one solution. But again, this is on the storage part, right? You also need the kernel. So you need two different kernels to do this.
But SQL Server already has capabilities like for column and row store. So in a way, those kernels are written, right?
Oh, I'm not sure.
I see.
So you need a completely different kernel. You cannot reuse anything that you have in a row store. You have to do a completely different implementation. And there was a guy in MIT that did exactly a PhD just on that. He said, can we take a row store and make it a column store just by storing data differently and moving them in? And the answer is no. It's not efficient. It's
sorry, but you are saying that Oracle has a column store implementation or SQL Server. In fact, I know SQL Server has a column store implementation.
I know that everyone has a column store implementation. Yeah.
So you take one of the instances of SQL Server and you run it on server A. You take another instance and you run it on server B.
Oh, that's perfect. Yeah, that's
with some middleware in the middle. Now, I do appreciate the fact that middleware can be a bit
complicated. Yeah.
Right?
Sure. But again, so that's one great solution. But then again, you're not optimal. And okay, we can discuss if you want to go optimal.
Simple. But it's very simple.
Sure. It's very simple. But at least what I see that people in industry are doing, and is that they're trying to move into hybrids. So they're trying to move into both into storage and to execution into hybrids because it helps with compression, it helps with execution performance. So yes, this is one first solution that you can do as your first version, but you're not going to stick to that, I'm sure. Okay, last slide, maybe. If you're wondering how this compares to a normal index, if you would build the index up front and then just you do very fast queries that take microseconds. So this is the same experiment in all graphs. This is just the first 10 queries, the first 100 queries, and this is the complete picture. And this green curve here is what the normal index looks like, and this is cumulative cost. So this is adding the first and the second and third and so on. So you see that even after 10,000 queries, building the complete index has not amortized the cost over doing cracking. So that's as an indicative, the way we think. We don't want to spend a huge cost in the beginning and still be very fast here, because you see how this comes down. This is answering queries in terms of microseconds. But even after 10,000 queries, it has not amortized. This blue curve here is yet another technique that we have in an algorithmic way for adaptive indexing, this AM, adaptive merging it's being called, which you see you have sort of an intermediate cost here, but then it has faster queries than cracking because it comes faster. But and the whole research here that we do is we're trying to balance how much effort we put up front with how much and much faster we can converge into what would be the optimal performance of a full index. And yeah, I may be closing with this challenge.
So, if I think of sort of some kind of data flow diagram with tuples or things flowing through operators, then I think what you're saying is that the operators near the leaves, they can, as it were, reach back and reorganize the data they're getting from.
Exactly.
But the operators deeper in the tree, they can't really reach back or do they reach back and reorganize the data sort of into somehow pushing back through the previous guys, right? Or is it just the leaf ones that do this reorganization thing?
So there's two answers. There's just the leaf ones.
Okay.
That's one answer. But then the second answer is that you remember I was talking about materializing these intermediates.
Uh-huh.
So this can be an overhead, of course, but it's also an opportunity because you can materialize these intermediates and then you can keep them, so you can remember them in the future, so you can reuse them.
I see.
So you can reorganize them and you can keep them for future queries. So you can play the same game on the intermediates.
On cached intermediates.
Yeah.
Okay.
Yeah.
Say your speaker.